everyone. My name is Alex Schexner. I'm with my group mates Caleb and Nathan. We're going to be going over our project of matrix of simulation scheduling, given it to us by civil engineering doctor candidate named Fahad Salahat. This is our 625 project proposal. This is the overview for our project. So in the beginning, our project is established on an existing codebase for LS-DYNA, which essentially is a crash simulation software. We can go over it later. Our project is currently written in Python. It's executed on a Slurm cluster. Being in 625, I'm sure we all know what Slurm is and how allocation for various nodes will work. It takes several crash parameters from a key file that the user can change for all the different types of iterations that we might need for trucks, barricades, as well as angles of attack, so on and so forth. It stitches together results in an LS prepost, which then takes all the parameters and the 3D rendering and puts it into its own software to establish the crash scenario. Some of the problems with this current workflow is that it is slow and inconsistent. That is one of the main problems that Fahad wants us to deal with. He thinks that his codebase is pretty much it's good so far, but we need to optimize it to make it faster. Some of the sub problems are the current deviation of execution is up to 2 hours for identical scenarios. So if one scenario, for example, runs, it takes 4 hours for it to run. The problem that he's having is that he executes the same scenario over and over. It can go up to like 6 hours instead of 4 hours, and that's currently not really optimal. So we want to change that, as well as suboptimal execution time of application. So if we run the whole software application of different scenarios, Fahad says it takes like 5 to 6 days roughly for it to execute, which is also not very optimal. We want to lessen that time through parallelization, which we'll talk about later, as well as inability to modularly cancel a group of calls. So currently, if we want to cancel something, it cancels the entire workflow, which is not optimal. We want to change that as well. And pre-post requires moving away from a computer cluster, which is one of the things that we want to make sure we get that done as soon as possible. So what is LS-DYNA? LS-DYNA is a general-purpose 3D physics simulation software. A little history about it. It's developed in Lawrence Livermore Laboratory. The original design for this was testing nuclear weapon impacts. I think it was roughly the 70s or 60s or 70s when it was being implemented. Now it's moved on to more convenient and applicable uses for modern day companies. It can support general finite element analysis on supercomputers, aka through Beocat. It can utilize different material models for different simulations. Some of what is currently mostly used for today. Automotive crashes and occupancy safety is one of the main ones that it's used for currently. If like having a automobile manufacturer would be vital to have this type of software to measure how safe their automobiles are and how to improve them, as well as explosions through military mine-shaped charges to see how its impact and how it better can be applicable through changing them for the good, as well as large deformation analysis for like earthquakes and things like that, as well as waves and tsunami impacts. And this is our reference at the bottom for where we found this information. It's also in our reference slide at the end.
Now that we've understood kind of what LS-DYNA is and what it has been used to do, we can take a look at what an actual 3D rendering scenario would be in terms of this project. On screen we can see that there are multiple different things. First, we can see that there's a barrier running along the side, and then there is also a vehicle in which the vehicle is striking the barrier. The vehicle itself has multiple different parts to it, and we can see that they're identified by different colors of the vehicle. This right here, I believe, is just some clipping. I think that this is all part of one trailer. We can see that the tires are broken up into different pieces, in which there are 1, 2, 3, 4 different pieces here. The cab is also done the same way, in which it allows us to have multiple different data points that allow for different crumple zones and data to be recorded throughout the car. The main issue that comes from these models is they have a high data point, or they have there's a high amount of points to calculate per model. And for instance, there could be hundreds, thousands, if not millions in this single model. I don't know off the top of my head. But we also do have another model, which is a smaller truck, which does take less time to compute, but it still takes quite a bit. Next, we can look at why there are currently no applicable solutions. There have been currently no attempts made to parallelize existing code, in which we mean that the techniques do exist to parallelize the LS-DYNA calculations and executions, but the requester currently lacks the ability to effectively batch schedule and parallelize the code, so that is the reason we have been brought in, as said by Alex. As well, Python actually limits the available options for parallel multi-core, and allows us, or it restricts on what we can actually use. So it's actually a good thing that we did cover MPI in this class. Next, we actually found another paper documenting the implementation of MPI with LS-DYNA, and while it didn't give a explicit solution, it was able to actually show us that MPI does work with Python and that it's accessible through the SciPy library, and we were able to see how it splits the workload. Continuing on, that paper was a paper from a conference that was done by Oleg and Andriy. I'm not even going to bother attempting the last names. It discussed the parallel calculations in LS-DYNA, in which they implemented MPI to improve the performance for their solution, I guess you could call it, and allowed them to actually bring down the runtime of their program quite significantly. Granted, this only discusses that it is theoretically possible based on their information gotten from the multi-core implementation that they did, but we believe that this can be implemented in our solution through Python.
So for our solution, we are planning on refactoring the given code base from Fahed through a collaborative manner. That starts by creating a GitHub repository. Like pretty much any project for our classes, GitHub is just always a place to go. Then Fahed asked us to specifically focus on a file in this code base called input files and command files.py, and more specifically on a class that he used for creating and organizing the .k key files previously mentioned. So the create class sets up and goes through a bunch of nodes on the civil engineering server and just organizes those and executes jobs. We believe that that can be done better through a bash script, which I'll talk about later. And then finally, we will need to possibly implement and utilize the MPI techniques on some other classes from Fahed. That depends on just how the actual code itself is structured. From what we've seen on the input files and command in the create class, we believe that this can be restricted to just that class. We will just have to spend some time looking at the other portions of the code base to see if any MPI changes are needed for that, however. And then we will create a bash script for batch scheduling. So the reason we like bash for this project is it gives Fahed an easy way to schedule his jobs in a programmatic manner. Bash supports operations like a for loop, so you can easily input multiple parameters there and call the execution of your code in one line, and it'll get executed multiple times via that for loop. It's supported by Slurm. It's what we've been using for all of our projects so far, so we have familiarity with it. The scripts are easily edited in a text editor, and it's very easily run through Slurm, so we believe that that will be the best form factor for part of the project. Additionally, Fahed had asked for the ability to cancel certain jobs if he realized he had made a mistake in scheduling the parameters. The ability to cancel some of the jobs without canceling everything in the SBatch run was something that appealed to him greatly, and so we believe that calling a single SBatch run and using a for loop, but then calling an srun command opposed to a second SBatch gives that type of flexibility and would allow for Fahed to either programmatically cancel that or even just go through and grab the job number and cancel it kind of in a slower manner. So, how does our solution solve the problems outlined by Fahed?
as previously stated, we believe that parallelization and the introduction of SBatch will solve all of Fahed's problems. Parallelization handles his two biggest concerns of having a slow overall runtime. Because of the code being set up in a serial manner, it just can take forever to do task after task after task when a lot of those tasks can be done at the same time and independently. So inherently, parallelization should allow for a speed up of the crash scenarios. Additionally, because we are spreading the code execution across several pieces of infrastructure, we can run into issues with hardware locking, resource locking, but the overall increase of access to different resources should more than offset that and allow for a more consistent hardware allocation and runtime across a bunch of different nodes, as opposed to kind of just pulling the bad luck of a draw on a slower node as opposed to a faster node. And that should allow him to have very consistent runtimes and overall faster runtimes. Then using SBatch commands will allow for the modular canceling as previously touched on via srun and then the scancel command through Slurm. And finally, the last useful part is that this should shorten his runtime of mass SBatch scheduling into a much more condensed time. Instead of having 5 to 6 days to run multiple scenarios, he might get down to 5 to 6 hours to run multiple scenarios, as opposed to the 5 to 6 hours he's currently taking to run one scenario, which should be a massive boon for him. So in conclusion, our implementation should solve Fahed's problems, as previously mentioned on the last slide, where we will fix a poor execution time, a very variable execution time, and the kind of monolithic scheduling problem where he can't cancel a run without losing all progress he has. So we believe Fahed will appreciate that. And then we're going to do that by implementing MPI multi-threading inside of Fahed's existing code base and using SBatch and srun batch scheduling and scancel to modularly handle the run of a parallelized execution. If anybody viewing has any questions for this, we are all accessible on the CIS Discord under our names of Caleb Nehus, Nathan Wells, and Alex Schexnader. Otherwise, have a good day. Here's our references. We referenced that conference paper from Oleg and Andre, and then everything else we pulled from talks directly with Fahed and through the LS Dyno Wikipedia page, just to get a bit more of an expansive context on the problem.